Hi, this is a tutorial on mapping in the default language in Sema. Mapping is a process that we need to perform usually very frequently in computer music. Mapping is when we need to take the output from one process and use it to control another process. An example could be taking the output of a low frequency oscillator and using it to control the frequency of a filter. Another example could be taking the x-coordinate of your mouse movement and using it to control the resonance of a filter. Another example could be taking the output from a machine learning model and using it to control sound. Very often when we're linking one process up to another, the ranges of the numbers don't always match up, so we need to do a bit of math in between to make sure that we can link things together in an effective way. And you can think of the mapping tools in Sema as a kind of multi-tool or Swiss Army knife of computer music process. We need to use them a lot, so it's really good to understand what these functions do. So let's start with a typical mapping problem. Here I've got an oscillator. It's a pulse oscillator, and it's running at 50 Hz, being stored in this variable osc. And then I'm running this through a state variable filter. So it's taking this oscillator as an input. It's got a frequency of 500, resonance of 1, and we won't worry about what these numbers mean in the context of this tutorial. So let's run this and see what it sounds like. Let's try varying. What we're going to do is do a mapping to the resonance here. So let's have a listen to what happens when you change the resonance. As I move it up, you get a kind of thinner, small resonance sound. So let's say I want to add some more movement to this sound. So I'm going to get an oscillator to do that. So let's make an oscillator, we'll call it LFO, standing for low frequency oscillator. And let's start off with a 1 Hz sine wave. So we can just plug this straight into the resonance. It's probably not going to work, and we'll see why in a minute. But let's just see what it sounds like anyway. So something pretty much went wrong there. And the reason is because the output of a sine wave is in the wrong range to control the resonance here. The output of a sine wave in the Sema system, the output of all oscillators go between -1 and 1. But the resonance here, it probably sounds good in the range maybe 1 to 50, 1 to 100. So we need to convert this sine wave into that range. And here's how we do it. We use a function called blin. So what the B stands for here is bipolar. So we know that a sine wave oscillator has a bipolar range, that is, it goes from -1 to 1. A unipolar range would be from 0 to 1. And then this takes two parameters, so our bipolar signal, and then the range that we want to map it into. So let's try 1 to 50, see what that sounds like. Now if I run this code, hopefully it's going to sound a bit better. So immediately we can see that it's something better is happening than last time. Last time it kind of blew out. So we can change these ranges. We can change the speed of the oscillator here. Let's just change that to half speed. So this is the mapping happening here basically. It's taking this bipolar signal and mapping it into a range that's useful for us to control the oscillator. The linear bit here says that the destination range should be a linear mapping into the destination range. The opposite we can do is into an exponential range, where we'd use the function b/exp. And you want to use exponential ranges basically when you're mapping to frequencies. That's the most common use for exponential ranges. So let's have a look at an exponential mapping instead. So we've got an example here in the tutorial. Let's just load that up. So we've got a LFO. Again, it's a 1 Hz sine wave, and it's being mapped exponentially into the range 50 up to 5,000. So this is frequencies here. And then we've got the same oscillator and filter here. This time the resonance is fixed, but we're using the LFO to control the frequency of this filter. So let's have a listen to what this sounds like. And again, we can kind of play with the mappings. We can keep the frequencies really low, just mapping 50 to 100 or something. Wide range. What we could try is to look at what happens if we do this linear instead. So it'll still work, but it won't sound as good. And that's because we need the exponential mapping to create more sensitivity in the lower areas to map to frequencies. So when we're back in exponential, we can hear that's kind of covering the full range of the frequencies. Let's have a look at the next two functions. So again, we've got linear and exponential mappings, but this time for unipolar signals. So a unipolar signal is something that lies between 0 and 1. A typical thing here, let's just stop the sound, would be a phasor. A phasor is a cyclic oscillator that rises in a ramp from 0 up to 1, then drops down to 0 and rises up to 1 again. It's very useful for control signals. And because it's in the range 0 to 1, we use U-lin, which means that it's a unipolar signal, and this time we're mapping it into a linear target. Let's see what this sounds like. So we're mapping this into the resonance here. Let's have a look at the exponential version instead. So again, exponential mappings are good for frequencies. So here we use this phasor to control the frequency of this filter using an exponential mapping. The phasor is going very slow, it cycles once every 10 seconds, and it's going between 50 and 10,000 Hz. We could try a different unipolar source, which would be the mouse, for example. So if I take that down to there, if I put a mouse X here, then I'm using my mouse to control the frequency. Or I could try mouse Y as well. So U-lin these U and B functions, the bipolar and unipolar functions, are essentially shortcuts to the fuller version of these mapping functions, which are lin-exp and lin-lin. So when we use these, instead of assuming the range of the source signal, we can actually specify it. So here, for example, we're using a phasor as a source signal, and we're specifying that its range is in 0 to 1. Or here we're using a sine wave signal as a source, and we know that that's between -1 and 1, so we're going to specify it to this function. Let's just have a listen to what this sounds like. We've basically got an oscillator, and we've got a bunch of control signals being mapped into controlling different parameters of this filter. That pretty much covers the very basic tools for mapping in the Sema default language, and you'll probably find yourself using these functions quite a lot, so it's good to go and get to know them.